subscribe.
Hey y'all, welcome to our Unit 6 review. Let's go ahead and jump right into it. Number 1 says write the vectors as a linear combination. So that means rewrite it like with the I and j. So the first one would be 1i plus 2j minus root 3. Oh, this is going to be kind of hard to do with text, so let's let's try that again. Make this a little bigger here. Okay, so round 2, 1i, and really you don't need the 1 there, so I'll go back and delete it, but just so you can kind of see how this plays out. Let's get rid of that thing. There we go. So 1i plus 2j minus root 3k. And usually when you write these as a linear combination, the I, j, and k are written just slightly differently. So basically you'll write them with like these little hats. And it's really just to differentiate it from any other variable. Like I, for instance, is typically used to notate an imaginary number, and we just want to be clear that that's not what we're talking about. The I, j, k are the standard unit vectors. So there's 1a. You don't really need the 1 as a coefficient, so if you write it like without the 1, that's fine too. And in fact, that's a little bit more traditional. For B, we've got 0i, so 0i plus 4j plus 1k. And we can simplify this a little bit. We don't need to write the 0i, since 0 times anything is 0, so we can just delete that. And then we don't need the 1 as the coefficient. So if we're trying to write this as efficiently as possible as a linear combination, it would look like this. Let's put the little hats on there. Okay, C, we've got negative 2i plus 0j plus 17k. Again, the 0 term is just going to go away. And then I'm going to rewrite the I and the k to have these little party hats on. Okay. Number 2 is having us go in the opposite direction. So they're giving us a vector written as a linear combination of standard unit vectors, and it's asking us to rewrite it in component form. And if it's just, my opinion, I kind of like component form better. You do want to be comfortable and fluent with both of them. Don't get too uncomfortable when you see the I and j, or vice versa. But you really want to just make sure that you're comfortable with both, so that you can read and understand what I'm trying to say. But yeah, if I had to pick one, I would just go with the component form. And you'll see as I go through this that is what I'm going to sort of default to on most of these problems. Here we don't have an I, so the first component is 0. Second component is negative 6. And then finally we can see that we've got a 3-dimensional vector here. I has a coefficient of 1, and then we've got 3 and negative 12. So hopefully these answers are going to be pretty self-evident here. Number 3 says that vector x has an initial point at 416 and a terminal point at 1006. Write x as a linear combination and component form. So what we have to do is figure out what the change in each component is, and those will represent the coefficients of our linear combination. So, like for instance, in order to get from 4 to 10, I've got to add 6. So the first component will be 6. So 6i. To get from 1 to 0, I've got to subtract 1. So I'm going to say minus 1j. And then finally, to get from 6 as our z coordinate, 6 to 6, well, I don't actually go anywhere, right? Like there's no change there. So the final component would be 0. And so I'd say like plus 0k. I don't need to write the 0k just like I don't need to write this 1. So just to kind of clean this up a little bit, I'm going to say 6i minus 1j, and then just leave the rest of it blank. Put the little party hats on, and now we've written it as a linear combination. So, like I said before, I kind of prefer the component form, like with the vector brackets, just personally. So if I have a choice, I'm always going to go with that. But this one specifically asks for a linear combination, so that's why I'm writing it with the I and j. Okay, number 4 is asking us to find the magnitude. So this is where we use the Pythagorean theorem to calculate the magnitude. Recall that the magnitude is really just the length of the vector. So this will equal the square root of 1 squared plus 2 squared. And 1 squared is 1, 2 squared is 4, 1 plus 4 is 5. So this will equal the square root of 5. And that will be the magnitude of this vector. For B, just be careful here. Notice how there's no I component. So, I'm going to go ahead and write the 0 squared, although obviously you don't really need that because 0 squared is 0. But here I've got 0 squared plus 6 squared. And if you're, trying to be super accurate, you could say negative 6 squared. But anytime you square a number, regardless of if it's positive or negative, the result's always going to be positive. So that's why most of the time when I'm just handwriting this and working it quickly, I'll just put 6 squared. But this is fine too. Either way, I'm going to get 6 squared is 36. Square root of 36 is exactly 6. So the magnitude of this is 6. And for 4C, we've got the square root. Well, actually, we've got a 3-dimensional vector here. So if we want to find the magnitude of a 3-dimensional vector, we're just going to basically use kind of an extended Pythagorean theorem here. And really, this formula is based on the Pythagorean theorem, although it's really a combination of two different right triangles put together. It's something we talked about in class. So let's go ahead and square all these up and add them. This would be 16, and 16 would be 32 plus 49. Okay, so I'm just going to break out the calculator here. It's a little bit too much for my brain to handle. So just to be on the safe side here, let's turn this on. And we've got 4 squared plus 4 squared plus 7 squared. 81. Oh, how about that? So we actually get another whole number for our magnitude here, because the square root of 81 is 9. Okay, let's take a look at number 5. Number 5, we're trying to find a unit vector in the direction of the given vector. So to find a unit vector, which is just a vector that has a magnitude of 1, we need to divide each component by its magnitude. So first, we'll find the magnitude, and then we'll divide each component by that magnitude. So let's first find the magnitude. So we'll say the magnitude of vector v, and I don't know if I can actually get a vector symbol here. Oh wait, yep, looks like I can. How about that? No, it doesn't like it. Even Cami, with its own notation, cannot get the arrow to look right on here. So disappointing. Okay, come on, Cami, you need to update that. Anyway, we got the magnitude of vector v is going to be the square root of 1 squared plus root 3 squared. Okay, so when we square root 3, or negative root 3, either way, we are going to end up with a positive 3 there. So, looks like I'm going to have to make this a little smaller, make it fit. So the magnitude of this vector is going to be 1 plus 3 is square root of 4 is 2. Right, let me double check that. Yeah, 3 plus 1 is 4, square root of 4 is 2. So that's going to be the magnitude. So the unit vector in the direction of v is going to be each of those components divided by the magnitude. So we've got the original vector, which is 1 comma negative root 3. And then if we divide both of those by the magnitude, 1 divided by 2 is just 1/2, and negative root 3 divided by 2 is just negative root 3 over 2. So there's our unit vector, which that coordinate should look a little familiar from last semester. Hopefully you kind of have a good idea of where that is and what that is on. Unit circle. Okay. Let's take a look at B. So we're trying to find a unit vector in the direction of V. Now, if you notice that this is just 2 units in the horizontal direction, so it's like going along the positive x-axis, you could probably find the unit vector without doing all this work. It's just going to be 1i, but let's go through the process just in case you don't quite catch that. So the magnitude of vector v for this problem is going to be 2 squared plus 0 squared. 0 squared obviously being 0, 2 squared is 4, square root of 4 is 2 again. Oh, interesting. So anyway, our unit vector in the direction of v, if I can get it to come up, is going to be, the original vector was 2, 0, so if I divide both of those by 2, 2 divided by 2 is 1, and 0 divided by 2 is just 0. So 1, 0, which is what we kind of expected at the beginning. So for C, we do the exact same thing with the 3-dimensional vector. Just make sure you know how to calculate the magnitude like we did with the 3-dimensional vector on 4C. You just basically use an extended Pythagorean theorem. So this one would be the square root of negative 4 squared, which is really the same as 4 squared, plus 4 squared plus 7 squared. So let's see, we got 16 and 16 and, oh wait, we already did that one. Oh yeah, it's this one right here. Okay, so we already did that calculation, it just comes out to 9. So we need to divide each vector by 9. So negative 4 divided by 9, 4 divided by 9, and 7 divided by 9. None of that is anything we can reduce. So this right here represents the unit vector in the direction of negative 4, 4, 7. So basically it's going in the exact same direction. It'll sort of lie right on top of it. The only difference being this will have a magnitude of 1 rather than a magnitude of 9. For number 6, it says find the direction angle in degrees of v. So this is where you have to use the inverse tangent equation. And then depending on which quadrant you're in, you may have to add 180 if you're in quadrants 2 or 3, or add 360 if you're in quadrant 4. So this one right here is in quadrant 2 because we got a negative positive. So whatever we get for that inverse tangent, we're going to have to add 180. So theta, in this case, is going to be the inverse tangent of 2 root 3 over negative 2. So we can actually simplify that a little bit. You don't necessarily need to because we're going to type it in the calculator, but you could. And then since we're in quadrant 2, we need to add 180. Yeah, simplifying this gets you, 2 divided by 2 is 1. So that's just really negative root 3. So when I go to type that in the calculator, I don't need to put the 2's in there. So just to kind of save a couple button presses here. Now before you put this into your calculator, make sure that you are in degrees. If not, this would be pi for instance, but the directions do stick to degrees. So I think pretty much all the problems are going to be in degrees, except for maybe like one of those solving. Be prepared when you solve an equation to be in radians, but most of these should be in degrees. So I'm going to hit mode, make sure I'm in radians, make sure I'm in degrees. And let's exit out of there. And so I'm going to go ahead and type this in. Now, I'm going to type this in separately just so that you can see what happens if you don't add the 180. If you don't add the 180, we're going to end up with a negative angle, a negative 60 degrees. And so when we add 180 to that, we should end up in quadrant 2 as expected, and we do. We get 120. So theta is 120. So basically what this is saying is the angle measure's trajectory is 120 degrees. Uh, 6b, we are in quadrant 3. So in quadrant 3, you're also going to add 180. It's just that the inverse tangent is going to result in a positive angle measure. The reference angle will be positive rather than negative. So we will we'll end up with should end up with an equation, I'm sorry, an angle measure that is in quadrant 3. Greater than 180, less than 270. So let's see, we've got the inverse tangent of 1, or negative 1. So a negative divided by a negative is positive. So because both of these are negative, I'm just going to make the whole thing positive. 1 over root 3. Don't bother trying to simplify this number. Just go ahead and throw it in your calculator. You could use a unit circle on this particular one. But since you get to use your calculator, let's just go ahead and take advantage of that. So we get the inverse tangent of 1 over root 3. I am expecting a positive reference angle here. Oops. $30 degrees, and 30 plus 180 gives me 210. All right, so my direction angle for vector v will be 210 degrees. For letter C, we have, we're going to work this out exactly the same way. So now I'm getting kind of bored because, now 2-1 is in quadrant 1, and in quadrant 1 we don't have to add anything, right? Because the reference angle is equal to our, equal to the angle that we're looking for. So really we just have the inverse tangent of 1/2. Don't think this is going to be a nice clean angle like the last two, because 1/2, 1/2 is not one of our common ratios on the unit circle, so we should expect to get an irrational value here. And it should be acute because we're in quadrant 1. So let's double check here. Inverse tangent of 1/2, probably going to be, if I had to guess, like 70 degrees or somewhere like that. I was way off. Forget. Wait, yeah, no, 26 makes more sense. Okay, forget my prediction there. I didn't give it enough thought. But, yeah, because 1 is the y. I was thinking the other way around. Okay, so anyway, yeah, theta is going to be approximately 27 degrees. Okay, number 7, we've got vector W. Let's fix that notation. Again, Cami does not like the vector notation for some reason. And we're given the magnitude and the direction angle, and it asks us to write the vector in component form. So to find the two components, you're going to multiply the magnitude by the cosine of the trajectory for the horizontal component, and then you'll use sine of the trajectory for the vertical component. But for both of them, you're going to multiply by the magnitude, which is 2. So this is going to be how we set up our vector, and we just need to calculate this out. So let's go back and review using the unit circle what these would be. So at 240, the coordinate is, let's see here, negative 1/2 negative root 3 over 2. So you've got 2 times the cosine of 240, which is negative 1/2, and 2 times sine of 240, which is, let's see, negative root 3 over 2. And so when I simplify this, essentially what happens is our, 2 divided by 2 is just going to reduce to 1. So these kind of cancel out. And so what we end up with is -1. All of a sudden we switched over to blue here. Let's try to fix that. So yeah, -1, comma, -√3. And that would be the vector that has a length of 2, or a magnitude of 2, and is pointing towards 240 degrees. Over here on page 2, we are trying to sketch all of these vectors. It says use the vectors below to answers 8 through 18. So it looks like we're going to be answering a bunch of questions regarding these vectors. And the first part here is to sketch each one. So I'll just go through and give myself some labels here. So here's A, B, C, D, and then it looks like I've got F, G, H, and M. These vectors are written in component form, so they don't have the I and the J like you would see in linear combination form. All right, so A is 0, 2. So for each one of these, I'm going to just throw on a little coordinate, both the X and Y axes, and give me like some blank space to work with on all these. Okay, so A is 0, 2. And the horizontal component comes first, the vertical component comes second. So you're going to go 0 units in the X direction and 2 units up in the Y direction. So this particular vector will look like this. And it's often helpful to label the grid too. So you can see it's 0 units to the right, 2 units up, and so there's vector A. Vector B is going to look very similar, except it's moving 2 units to the left. So it's going to look more like this. C is going 2 units to the right and 2 units up. So we're going to draw the arrow pointing towards the coordinate 2, 2. D is 0, -2, so 0 units in the horizontal, 2 units down. This is going down towards the negative y-axis. F is -2, -2, so 2 units to the left and 2 units down. Oh, wow, jeez. There we go. All right, that one took a little while longer. All right, G was 2 units to the right and 0 units up or down. H is 2 units to the right and 2 units down. And finally, M is 2 units to the left and 2 units up. So we pretty much have these smallish vectors. They're not all 2 units long. Some of them are. These vectors that are going alongside one of the axes, like A and B and D and G, those all have a magnitude of 2. And so you can see that the length of that vector is 2. But the ones that are going diagonally, like C or F or H or M, their magnitude is not 2. To measure their magnitude, to figure out how long this diagonal line is, we'd have to use Pythagorean theorem right here. And so it'd be 2 squared plus 2 squared. So 4 plus 4 would be 8. So it's √8 units long, which is not equal to 2. All right, so now that we can see what all these vectors look like visually, we can start to get a sense of, why the arithmetic that we do makes sense. So down here, where we're using operations to combine these vectors, I'll refer back to the picture so that you can see what the solution will look like. So for here, we've got a plus d, and a is 0, 2, and d is 0, -2. When I add these, what I'm really doing is just combining the corresponding components. So I just add, like in columns here, 0 plus 0, which is obviously 0, and then 2 plus -2 is also 0. So kind of interesting here, we end up with the 0 vector when we combine those two vectors using addition. Let me go ahead and box that. There we go. So let me show you why visually as well. So if the first vector is 0, 2, then we go 0 units in the x and 2 units up. And since d is 0, -2, the way that we add vectors is from head to tail. So I'm going to start sketching out d, but starting where a ended up. So I'm going to use the terminal point of a as the initial point for d. Since d is 0, -2, and I'm starting here, I'm going to go 0 units in the x direction and 2 units down. And where I end up pointing back to is this point 0, 0. For 10, we've got c plus h. c is 2, 2, and h is 2, -2. So we've got 2, 2, 2, 2 for c, and then h is 2, -2. I'm also adding here, so I'm just going to add my columns like I did in number 9. So we've got 2 plus 2, which is 4, and 2 plus -2, which is 0. So the resultant vector, c plus h, is 4, 0. Here's what that would look like on a graph. The first one would be 2, 2, so its terminal point would be exactly there, 2, 2. And then when I add the second one, I'm going to start at the endpoint, like at the head of this other vector, and use that as the tail of the second vector, and move 2 units to the right and 2 down. So I need to put a couple extra dashes here. But notice how I end up at 4, 0, which is what we ended up with. So here we can actually see the resultant vector. We couldn't over here because we ended up getting the 0 vector. But here we can see the resultant is right here. So just to illustrate this a little bit better, this is c, this is h, and down here we have c plus h. Here we have the magnitude of vector c. So vector c is this one right here. It's 2, 2. And when we're calculating the magnitude, what we're actually calculating is the length here. So I kind of already gave it away earlier when I was talking about the lengths of these vectors. But the way you compute the length of the vector is by just using the Pythagorean theorem. So we've got the square root, where's that square? There we go, of, since c is 2, 2, we will use 2 squared plus 2 squared. Two squared is 4. So 4 plus 4 turns out to be 8. So this is the magnitude of the vector. So one thing I want to make just a quick mention here is notice how the answers to 9 and 10 were both vectors. When you find the sum of two vectors, you end up with a vector. But when you calculate the magnitude of a vector, you get a scalar. So 12 and 13 and 14, we're doing the dot product. And we've talked about what the dot product represents. I'll show you the illustrations and kind of repeat myself as we go through these, just to really hammer that home. But for number 12, we've got B dot D. So the way we calculate dot product, if we know what the components are, is we multiply the corresponding components and add those two products together. So we got -2, 0, dot, and then D is 0, -2. So like I was saying, we're going to multiply the corresponding components. So -2 times 0 plus the product of the vertical components. So 0 times -2. And I'm just going to throw the -2 in parentheses just to emphasize that this is not -2. So -2 times 0 is 0, and 0 times -2 is also 0. So 0 plus 0 is 0. We end up with a dot product of 0 here, which is notable because that means that these vectors are orthogonal. Or in other words, like the lines that they lie on are perpendicular. And we can see that if we graph these. So B is this one right here, and D is this one over here. And so you can see that, yes, in fact, they are perpendicular, which means B and D are orthogonal. And that might not even be worth like making a note of here, because we'll talk about that later. For number 13, we have B dot G. Okay, so we've got B and G. B is -2, 0, and G is 2, 0. So we've got -2, 0, oops, dot 2, 0. So we're going to multiply the corresponding components and add them together. So -2 times 2 plus 0 times 0. -2 times 2 is -4, and 0 times 0 is obviously 0. So -4 plus 0 is just -4. So that is going to be the value of the dot product. Let's take a look at B and G, and hopefully I can put some context around what the -4 actually is representing. So there's B and G is over here. Okay, so this one's kind of interesting because we can, we talked in class about interpreting multiplication using a number line, and we see here that our vectors really are just representing 2 times -2 here, right? There's no components going up or down, so when we multiply this number by the shadow that gets cast by the other vector on top of it, this shadow is like, it's like if you were laying down, your shadow would be exactly the same length as you were, but you're pointing in the opposite direction. So we have 2 times -2, which would be -4. Hopefully the next one will do a better job of illustrating dot product These two are kind of special cases here. Now 14 is S times W. All right, well, there's no S and there's no W here. So, all right, well, forget about it. I guess we're just going to omit this one. Okay, so 15, we've got 2 times b minus 4 times a. So we're going to have 2 times the vector b, which was negative 2 comma 0, minus 4 times vector a, which I cannot see at the moment, so let me scroll up. Vector a was 0, 2. So the way we're going to simplify this expression is first use the distributive property to distribute this scalar to each component of the vector inside. Okay, so 2 times negative 2 is going to be negative 4. 0 times 2 is 0. And then negative 4 times 0 is 0. And negative 4 times 2 would be negative 8. So at this point, we're going to add kind of like we did in 9 and 10. And I was kind of showing you this stack as a way to organize your work. But hopefully at this point, you can kind of see like which components to add up so that I don't have to like rewrite it like that. You have negative 4 plus 0, which would be negative 4. And you have 0 plus negative 8, which is negative 8. So the resultant vector here would be negative 4 comma negative 8. Number 16 says, find a unit vector in the opposite direction of C. Okay, so let me give you a little picture here before we start doing any calculations. Let's pull C down here. So C is 2, 2, and it's asking for a unit vector in the opposite direction of C. So the opposite direction would be like this direction, right? Now what we're looking for is a vector in that direction, so down and to the left, but that has a magnitude of 1. Okay, the magnitude of C here is root 8. We calculated that up here in number 11. So root 8 obviously is not the same as 1. So what we'll have to do is first find a unit vector in the same direction as C. And then we'll flip it around by essentially just multiplying everything by negative 1. So first, we're going to find a vector, or a unit vector rather, in the same direction as C. And the way we calculate unit vectors is we divide the vector by its magnitude. Essentially what we're trying to do is scale it down. So we're taking the length of the vector and then just dividing each component by it. Good about simplifying, rationalizing the denominator and simplifying the radical, but it's really not that necessary. So anyway, this is the vector that is going in the same direction. So if you want one that's going in the opposite direction, we need to multiply all of this by negative 1. So to get the unit vector in the opposite direction, come on, there you go. We're going to have negative 2 over root 8, comma, negative 2 over root 8. There we go. Okay, so that's our answer. Now, if you do want to go a little further than this and you want to completely simplify it, I'll just show you how, what that would turn out to be. So if you have root 8, root 8 is the same as the square root of 4 times 2. And the square root of 4 times 2 is the same as the square root of 4 times the square root of 2. And the square root of 4 is 2. So the square root of 8 is equivalent to 2. Now, so we would get the same thing over here. I could reduce this. 2 over 2 is 1. So this becomes 1, and this becomes 1, which is just, we don't have to write the 1. This also becomes 1. So we get 1 over root 2. And if we rationalize it, and by that I mean multiply both the numerator and the denominator by root 2, I would get, oops, I would get root 2 over 2 So if I multiply this by root 2 over root 2, I'd get root 2 over root 2 times root 2 is 2. And so this coordinate should look a little familiar. This is a coordinate on the unit circle, right, which is 1 unit away from the center, going down in this southwest direction. So like if you're imagining the unit circle on here, the vector that we just found was 1 unit in the opposite direction. I want you to think about what angle measure that is. Just think back to your unit circle. And that's why you should recognize this. Okay, this is the coordinate on the unit circle right there. So any of these solutions are fine. You can really just leave it like this. But if you want to see what it would look like rationalized and simplified, you would get this answer right here. For number 17, it says find a vector with length 6 in the direction of f. So to answer a question like this, first we're going to find a unit vector in the same direction as f. Oh, I guess I didn't copy that. There we go. And so we already know how to find a unit vector in the same direction as a given vector. We just divide the vector by its magnitude. So let's go back and check out what f is. And we're going to divide it by the magnitude of f. So f up here is -2, -2. Okay, we see the sketch over here. Might as well bring it down because I'm sure we'll want to talk about it. So yeah, it's -2, -2. And the magnitude of this vector is equal to the square root of -2 squared plus -2 squared, which is the same as all of these diagonal ones. It's root 8. So we get a very similar answer here because, I mean, we actually get the exact same answer because look at the vector we're trying to find here. We're trying to find the vector that is exactly 1 unit away from the center, right? This unit vector. Now that's not going to be our final answer for here because we're trying to find one that is of length 6, but this little interim step is going to give us the same coordinate that we got over here. So we're going to divide each one of these by that root 8. And then if we want a vector that is of length 6, what we need to do is we're going to scale up this vector we just found, right, which is at -√2. Actually, we can probably see it nicely if we draw a little circle on here. No. That's probably close enough. So say that's the unit circle. The vector we just found is this one right here, 1 unit. It's the unit vector in the same direction of, not C though, of F, this one. So what we're really trying to find though is one that has a length of 6, not 1. But you have to find the length of 1 first so that you can scale it up. Or I shouldn't say you have to, but I think it's a lot easier to scale this down to the unit vector and then scale it back up to whatever the desired length is, which in this case is 6. So we're going to multiply each one of these components by 6. So instead of it being a unit vector, it will be a vector with magnitude 6 in the same direction as F. So we're now talking about a vector that, you know, it doesn't have a length of 1 or 2 or 3 or 4 or 5, but 6. It'll be a little bit out here. This is just an estimate, but you can see it should be bigger or have a larger magnitude than the other two vectors. So we just multiply each one of these by 6. Negative 2 times 6 is, what would that be, negative 12, and the same thing goes over here. So we would have, maybe I should spell this out a little bit, 6 times this vector, and then we're going to distribute the 6 to each component. And so our final answer here would be negative 12 over root 8, comma negative 12 over root 8. And you could rationalize and simplify, but again, it's not really going to be necessary. Oops. Okay, well, there's number 17, and that's the end of the second page. So let's move on to the third page. Number 18 is asking for the angle between these two vectors. So we're going to get that by rearranging the formula for the dot product. So if we have dot product u dot v, one way to calculate that is to find the magnitude of each vector and multiply by the cosine of the angle between the vectors. So here's the magnitude of u times the magnitude of v times the cosine of theta here, where theta is the angle between the vectors, which is what you're looking for, the angle between the vectors. So I'm going to give you this formula right here, but you're going to need to know how to rearrange this so that you can find theta. So let's go through that process right now. First thing you'd want to do is divide both sides by these factors, the magnitudes of u and v. So I'm going to divide both sides by these magnitudes. And what I'm doing here is just trying to isolate theta. These will reduce out on the right hand side, and so you'll have u dot v divided by the magnitude, or the product of the magnitudes of u and v, and that equals cosine theta. Then to isolate theta here, you take the inverse cosine of both sides, and you'll end up with theta equals the inverse cosine there we go, of this expression. So this is going to be the formula that we use to calculate the angle between two vectors, but I'm not going to give this one to you explicitly on the test. I am going to give you this one right here, so you will need to know how to rearrange this to actually find the angle between the vectors. Or, you know, if you're just decent at memorizing formulas, you could just memorize this one as well. But no need to, because remember, it's coming from the dot product formula. So now we're going to calculate both the dot product of u and v, and we're going to calculate the magnitudes. We're going to throw everything in here and use our calculator to find this angle. So the dot product here is going to be 1 times 2 plus 1 times negative 2. The magnitude of u is going to be the square root of 1 squared plus 1 squared times the square root of 2 squared plus 2 squared. Or I guess technically negative 2 squared, but that shouldn't matter. You're probably safer putting in the calculator without the negative, just because you're squaring it. And just make sure when you're putting in the calculator that you put parentheses around the negative. Or you could just not put it at all, and you'll be safe too, because you're squaring it. So now something I'm noticing here before I jump to the calculator is this dot product is going to be 2 plus negative 2, which is 0. So as soon as I notice that the dot product is 0, I can calculate the inverse cosine of 0 pretty quickly. Using the unit circle, we can see that cosine of 90 degrees, or pi over 2 radians, is 0. And so that's going to be the angle between the vectors. So we can almost just stop right there. Anytime the dot product is 0, the angle between the vectors is going to be 90. But just in case you don't catch that, if you do go through and calculate all this, you get square root of 2 times the square root of 4 plus 4 is 8. So you get square root of 2 times 8, which is 16, and so forth. But so right here, we're able to say that theta is the inverse cosine, or I'm sorry, is equal to 90 degrees. All right, we're able to say that quickly because, without using the calculator, because we see that the dot product is 0, and the inverse cosine of 0 is 90 degrees. You can always test it. If you don't trust me, you can always bring up the calculator and say, all right, well, what's the inverse cosine of 0? Oops, I need to make sure I'm in degrees here. It just reported back pi over 2, which is why I'm getting this funky decimal. But there we go, 90. All right, so there's number 18. Number 19 is going to be similar, but before I move on, I just want to do a quick sketch of this so you can see and be convinced that the angle is 90. In fact, if you do the sketch first, you might catch the fact that it's going to be 90, just straight from the sketch. The first vector is 1, 1, so that would be like right here, pointing at this coordinate 1, 1, and then the next one is 2, negative 2. Hopefully it's already kind of clear why this is going to be 90. And there you go. So you can clearly see this is a 90-degree angle, and it's a good idea to do a sketch every time just so that you can have some kind of reference for judging whether or not your answer is accurate or not. You want to make sure that your sketch looks reasonable or reasonably close to what you get arithmetically. So number 19, we're doing kind of the same thing. I won't go through this whole process where we figured out what, the formula for theta here. You can just rewind the video and kind of go through that explanation. So I'm just going to jump straight to using it. And so we need to compute the dot product of u and v, which is going to be 1 times negative 2 plus 7 times 4 divided by the magnitude of u, which will be the square root of 1 squared plus 7 squared, times the magnitude of v, which will be the negative 2 squared plus 4 squared. So let's go ahead and simplify all this. see here, 1 times negative 2 is going to be negative 2. 7 times 4 is going to be 28. So negative 2 plus 28 is 26. 1 squared is 1. 7 squared is 49, so this is going to be root 50. And then we've got 4 plus 16. This is going to be root 20. So actually, 50 plus 20, or 50 times 20 is going to be 1,000. So this is actually going to work out nicely, I think. So let's go ahead and type this into the calculator. We have the let me make sure, still in degrees. Yep, okay, good. Don't want to make that mistake again. Inverse cosine of this fraction, 26 divided by root 50 times root 20. Okay, so I get approximately 35 degrees. So let's sketch it out and just make sure that that seems reasonable. All right, so we've got 1, 7 and negative 2, 4. So let's see, I'm going to need, yeah, it should look something like this. So we've got 1, 7, 1, 1, 2, 3, 4, 5, 6, 7, and we've got negative 2, 4. So the first vector, vector u, is going to be like pretty much up here, and vector v is going to be negative 2, 4. It's going to be roughly here. So you can see that 35 degrees seems pretty reasonable for this angle measure right here. All right, down here we've got these vectors not in standard position, so we don't even know where the origin is. But that's not going to stop us from knowing what these vector measures are. So like C, for instance, would be 2, 2, where U would be 2, 0. V would be negative 2, 0. W would be it would be 0, 2. T would be negative 2, 0, and so forth. So you can still name these or say what their components are pretty easily from the graph, even though they're not in standard position. 40 says 4a plus x equals 5c, find x. So basically what we have here is 4 times vector a, which is 0, 2, plus x. So I'm just going to call this like x1, x2. This is what we're trying to find. Equals, 5 times vector c, which you can see is 2, 2. Okay, so let's simplify this a little bit and see if we cannot figure out what this vector is. This is vector x. So we're going to first distribute the 4. Okay, multiply this scalar by this vector. We're also going to multiply this scalar 5 by this vector 2, 2. So 4 times the vector 0, 2 would be 0, 8 plus, and really we can just call this vector x. We don't need to give the components specific names. Well, maybe it won't let me do that. Cammy does really not like that these little vector symbols, but no worry. Okay. And then 5 times 2, 2 will be 10, 10. The next step is going to be to subtract this 0, 8 from both sides. So 10 minus 0 is just 10. And then 10 minus 8 is 2. So now we can say that this vector x is going to be 10, comma 2. So yeah, and really, we could just call this x. We don't have to write it as a vector, but we do want to include the vector notation, so I'll have to just handwrite that in there. There we go. All right, well, I can't seem to just grab this one piece over here. All right, there we go. Cleaned it up a little bit. Number 21 says 5 times w. So it looks like we're just going to be distributing a scalar 5 to a vector w, which is 0, comma 2. So we need to distribute the 5 to both the 0 and the 2. And we get 5 times 0, 0. 5 times 2 is 10. Number 22, we're just multiplying negative 3, this scalar, by vector c. So we've got negative 3 times vector c, which you can see is 2, 2. And we'll distribute this negative 3 in to get negative 6, 6. Or negative 6, negative 6. All right, so that's that little section. Number 23, looks like we're calculating some dot products. So recall that to calculate the dot product, you will multiply the corresponding components and then add those products together. So if I'm going to do a dot b, I'll have 2 comma 5 dot b, which is 7, negative 3. And you'll notice that I'm using component form for all of these, and that's just a personal preference. If you like writing them using a linear combination, that's fine as well. So we're going to get 2 times 7 plus 5 times negative 3, which is 14 minus 15, which would be negative 1. For b, we're multiplying c times b, so b is the same here. C is negative 4, 1. So we have negative 4 times 7 plus 1 times negative 3. We get negative 28 minus 3. So that'd be negative 31. For C, we've got D times F. So looks like we're finding the dot product of two three-dimensional vectors. And this will work pretty much the same way. The only difference here is that we have one extra product to add together. So we've got 2, comma 5, comma 3, dot 4, 0, 7. Make sure all that looks good. Yep, okay, so we've got our first components, 2 times 4, times our, or plus our, the product of our second components, 5 times 0, plus the product of our third components, 3 times 7. So that would be 8 plus 0 plus 21, which altogether would be 29. So you can see the three-dimensional vector multiplication works really the same way. Okay, you could have as many entries in these vectors as you want, as long as they're the same. You can find the dot product in this way. So that wraps up page 3. Let's take a look at page 4. Suppose that vector x is sine t comma 1/3 and vector y is 2 comma 3. What values of t would make x and y orthogonal? So recall that orthogonal essentially means that the vectors are perpendicular. So like we saw a couple different problems with orthogonal vectors, like here's a good example, number 12. We saw these were orthogonal. And really the key thing about them being orthogonal is that the dot product is 0, like we saw here. I thought there was maybe another problem where we had orthogonal vectors. What happened there? But I'm pretty sure we did. Oh yeah, we found orthogonal vectors here. But really what you need to know to be able to answer this question is that the dot product needs to be 0. Okay, so, and that's pretty much what the definition of orthogonal is. Orthogonal vectors have a 0 dot product. So we're going to set up an equation which is based on how we calculate the dot product. So we're multiplying the horizontal components, sine t times 2, and then 1/3 times 3. And we're going to add those together and hopefully get 0. So 2 times sine t is going to be just, well, 2 sine t. 1/3 times 3 is 1. Then we'll subtract 2 from, we'll subtract 1 from both sides. And so we'll get 2 sine t equals -1. And then we'll divide both sides by 2 to get sine t equals -1/2. So to figure out what the angle measures are, and this really we're just trying to find t, and there's no restriction on t here, so we're going to have to give the general solution. We want to find all of the angle measures where sine is equal to 1/2. This is something that you can find on your unit circle, so hopefully you can do a quick sketch of a unit circle. You know, I might just, do one right here just to kind of show you what I would do on the test. Here's a unit circle, and I'm trying to imagine where is sine -1/2. So sine's referring to the y coordinate, so -1/2 would be like roughly like right here, since this is -1. And so I'm looking for the angle measures where the y coordinate is -1/2. So that's going to be here and here, or at, let's see, that would be 7 pi over 6. Where's the pi? Here we go. 7 pi over 6 and 11 pi over 6. And as we know from previous units, solving trig equations, we have to put plus 2 pi n here to indicate that there are infinitely many solutions, all of which are some even multiple of pi units away from these two. So this is the best way you can answer this question. Occasionally I'll just ask for the angle measures on the unit circle itself, but this is what you would get. Okay, so that's 27. Let's take a look at 28. So 28, we're given the magnitudes of two vectors, and we're given the dot product of the two vectors. We want to measure the angle between the two vectors. So this, really what we're going to do here is we are going to use the alternate dot product formula and rearrange it a little bit to measure the angle between these two. So we did that before, which problem was that? Yeah, so we did that on 18 and 19. So if you want to see like how I come up with this equation given the dot product formula here, I'm going to kind of just skip through all the intermediate steps and do it on the current one, but go back to 18 where I kind of explain where this is coming from. The short version is that it's coming from the dot product formula, and then we were going to rearrange this for theta. So we would divide by both magnitudes and then take the inverse cosine of both sides, and we'd end up with theta equals the inverse cosine of the dot product divided by the products of the magnitude, or the product of the magnitudes. So this problem actually ends up being a little bit easier than the ones we did before, the 18 and 19, because on those we had to calculate the magnitude in the dot product, whereas here it's just given to us explicitly. So all we need to do, kind of cuts out all that intermediate work. And so we can just fill in here negative 93. Magnitude of u is given as 20. Magnitude of v is given as 6. And then just toss this all into the calculator, and that will give us the angle. So let's pull up the calculator and see what we get here. So it looks like we kind of have it already set up here. So we get the inverse cosine. Let me double check, make sure I'm in degrees, which I am. Okay, good. So the inverse cosine of negative 93 divided by 20 times 6, and we get about 141 degrees. Remember, and I'm going to keep hitting this every time we talk about angle between vectors. When the angle is obtuse between two vectors, the dot product's negative. So we saw we had a pretty strong negative dot product here. So these two are pointing, not towards each other. There's 141 degrees between them. When the angle is acute, you'll have a positive dot product because the two angles are basically pointing in the same direction. But here's our solution. The angle measures about 141 degrees. Number 29 and 30 are both work problems. So let's get rid of the calculator, although we'll definitely need it to do our calculations here. The formula we're going to use here for work is work equals force times, I want to use a little dot here, but okay, I'll just draw in a dot, times the displacement vector. So I'll put a little dot here. Okay, so we need to find the force vector and the displacement vector. These are going to be two vectors that are going to be implied in the problem. So let's see here. A toy wagon is pulled by exerting a force of 25 pounds on a handle that makes a 20-degree angle with the horizontal. Find the work done in pulling the wagon 50 feet. Okay, so we're going to pull the wagon 50 feet. So, and it looks like, according to this diagram, it looks like we're pointing to the left. So our displacement vector, since we're going to the left, is going to be negative 50, 0, because we're pulling it 50 feet to the left. Okay, so just to kind of add to this diagram, here's 50 feet to the left. All right, here's our negative 50, 0 vector. And it's a 20-degree angle with the horizontal, so 20 degrees as our reference angle means our angle that we actually want here is going to be 160. Okay. So we've got our angle measure, we've got our force, which is 25 pounds, and the way that we come up with the force vector is it's going to be the magnitude, or the force, which is 25, times the cosine of the angle measure, 160. So 160, comma, 25 times the sine of 160. So that is the force vector. So what we need to do now is just find the dot product of these two vectors. Okay, so we get 25 times cosine of 160 times negative 50 plus 25 times the sine of 160. Let's throw in that little degree symbol there. Times 0. So this vertical thing, this right here is just going to be 0. So we don't really need to worry about that. let's just go ahead and type in this left-hand part first. Now, 160, that's not going to be an angle measure on the unit circle, so you're not going to be expected to report back to an exact value for that. We're definitely going to round. So let's go ahead and type that in here. Now, the force and the direction are in the same. The force vector and the displacement vector are in. They're both pointing sort of to the left, so we should expect a positive dot product here. So let's see what we got. 25 cosine of negative 60, or 160 rather, times negative 50. Whoa, big one. All right, so we got approximately. So the work is equal to approximately, or here, I'll just type it like this. 1,170, I'll just round to the nearest whole number here. 75, and what are our units? We've got points. That is a typo. That I'm gonna go with pounds here. So yeah, a little typo there. And the distance is in feet, so these are going to be foot-pounds. If the units are measured in newtons and meters, like where the force is in newtons and the distance is in meters, you can say a meter newton, but really you should say a joule. It's got a special name there. And I think that we're going to see that on the next problem. Okay, so there we go. We do get a positive dot product, so that's a good sign. Now, just a little quick mention here, and I'm just going to kind of breeze through this, but you know, if you kind of work through this quickly and you accidentally use like 50,0 and 20 degrees, you're still going to get this right. Check this out. We'll still get 25 times the cosine of 20 times positive 50. Still get the right answer. So, you know, you can still get it right if you're not super careful about you know, what angle measure is actually getting pulled through. Like this particular problem, it doesn't say specifically that it's pulling to the left. I just kind of got that from the picture. But if you're unsure, I just want you to notice here, it doesn't really matter whether, you know, you're going to the left or to the right. You just have to make a decision, and based on that decision, if I'm going to the left, I'm going to use the 160 and negative 50. If I'm going to the right, I'm going to use 20 and positive 50. The amount of work should be the same either way. But I just wanted to make a quick point of that. So let's look at, looks like we got one last problem here, okay, where it's another work problem. So we're going to have to use that calculator at some point, but it says a force of 20 newtons is applied to an object at an angle of 25 degrees, causing a displacement of measuring 2,3. So we got the displacement vector is just explicitly stated. Okay, so let me pull my work from up here. The displacement vector here is the 10,2, and the force vector is going to be 20 newtons, so 20 times the cosine of 25 degrees and 20 times the sine of 25 degrees. 25 degrees is another angle measure that is not one of your common angles on the unit circle, so we will need to use a calculator for this. So let's go ahead and calculate the dot product here. So we've got 20 times cosine of 25 degrees times 10 plus 20 times the sine of 25 degrees times 2. And I'm just going to throw all this in the calculator. We don't get the advantage of having the vertical component or the vertical piece cancel out because we're not just pulling the wagon to the left, we are pulling it to the left and up. So, you know, we have to take that into consideration. But let's go ahead and just throw everything in the calculator and get our final answer here. We get 20 times the cosine of 25 degrees times 10, which is the change in in displacement horizontally. And then we're going to say plus 20 newtons times the sine of 25 degrees times 2. So we get our work is approximately 198. Like I was saying before, you could call these, if you're following the same naming convention as we did above, you would call it like a meter newton, but this particular unit of work has a specific name that we use instead of meter newton. We call it a joule. And so that's it for the review. You know, y'all, as always, reach out if you have any additional questions or just want me to clarify anything, or if you catch a mistake I make or anything like that, you know, please let me know so I can make those adjustments. But other than that, y'all have a great day, and I'll see you next time.